I was looking around to see if there was one really good description somewhere that was all together, condensed, that I could point you in that direction, and didn't find a really good one. We're going to encounter a problem here in that lots of the words descriptions sound similar to each other, and that we have two variables both called I. One's italicized, and that's in my book is a problem. And I was reading an article online where they switched and started calling I L, but then switched back to calling it I mid-paragraph. And that's the problem with websites versus textbooks. For everything that's wrong with a textbook, at least somebody has proofread it. When you go to a website, you don't know exactly what you're going to get. And then my background, I'm going to describe something as a mu, but that is often written as an M. In fact, I think I'm going to do, I think I've got it in my own notes. As a mu collectively, and an M when it's an individual. Yeah. So, this is where we are. Spin's a form of angular momentum. Turns out that both protons and neutrons, so it's, I think, easier to see that with protons, because protons have a charge, and if they're moving or if they're rotating even, they will be able to generate a magnetic field. These both have spin. We're going to give this a value I. It's the regular I. Which is why when we count protons and neutrons and electrons, for regular hydrogen, a regular hydrogen has a proton, no neutrons, and has one electron. That's not part of the deal here. So it has a spin, nucleus spin of a half. If I made this a deuterium, then I have one proton. Oh. One neutron and one electron. And now the spin of my nucleus is the sum of the spins of the individual particles, subatomic particles. That's a half for the neutron. Supposed to say what? Oh, yeah, no, no. I didn't finish my thought. It's equal to 1. And when spins are integer numbers, that makes them invisible to the NMR experiment. We're going to say that they are non-receptive. Spin half's great. Spin half is what we're hoping for. this is what we're going, this is receptive to NMR. And the really great thing about hydrogen 1 is that it's abundant. It is the big isotope of hydrogen. 99.9 something percent of all of the hydrogen on this planet is hydrogen 1, not hydrogen 2. And because it's wildly abundant, it's also in lots and lots of the samples that we want to investigate. So proton NMR, hydrogen NMR, gets to be the nucleus that we investigate the most. But it's not the only one. Let's have a think. If we pair protons and neutrons together, I have two real possibilities, and then each of those two possibilities is subdivided into another two possibilities. So if my mass number on the periodic table is, which way around am I going to do it, is even versus if it's odd, I can see two scenarios for this. Even mass numbers can arise when I look like this. That the number of protons and the number of neutrons are both even. If I have an even number of protons and an even number of neutrons, then my mass number, two even numbers added together, gets to be an even number. The other way I can make an even number is to add two odd numbers together. To get a mass number off the periodic table that is an odd number, well, there's two ways to do that. You can take an even number of protons and an odd number of neutrons, or you can take an odd number of protons and an even number of neutrons. Okay, so here are my four combinations to get the two outcomes. That is a mass number that is even or a mass number that is odd. The outcome is reflected in what the value of the spin I is. In cases where these numbers are even, those are no spin nuclei. When they're both odd, then I have integer spin nuclei. These are both nuclei that are not going to be of use to us. We're going to have to invent another technique completely to see those nuclei. Can't see them by NMR. Well, these two combinations give us nuclei that are half integers, which means these two be visible to the animal experiment. All right. Well, I could tell you, I could give you a list of nuclei, or I could have you figure it out. Go find some atoms that you might want to take a look at from the periodic table that might be in some molecules of interest to you, and then figure out if they will be visible to the experiment that we're trying to do. There's the big one on the wall, but there's particularly the unfriendly one.
Are you busy at 1?
Yeah, I talked to Dr. Hoffman yesterday. I was like, can I just use this for questions? Because it's just, she needs it. She's like, yeah, I can get math here until I recover. Okay, whatever. But I'm thankful that y'all are able to. I think Tali's gonna do it too.
She is. Well, if she's gonna cover, then I don't need to be there. I have stuff I have to do. I mean, I understand if you got work to do, but if
Yeah,
Tali-
Tali will do it, so just tell Doctor. Did you tell Dr. Hoffman? I told Dr. Hoffman you could be there, but just tell her, like, yeah, no, Tali's gonna be there.
yeah, because I have crap to write. So if Tali's gonna be there, there's no
I
need
just
for
don't see it. Well, I don't know why we need to do this too. It's literally just like that.
Yeah.
If she wants people to walk around and just, I don't do the math the way that she does it though, so.
No, I don't even remember the math of the last.
It's just C equals C, and then conversions, it's literally just that.
Yeah, because I was gonna use these 2 hours to our break to write applications.
Yeah, that's what I do too.
Yeah.
Is there any application?
What are you writing for?
Scholarships.
Oh, yeah, that's what I'm doing. I need to write the application. So it's probably gonna be, there's no point in me being there. I don't need to be.
Okay, what you come up with?
Well, calcium's a good one, but we can't.
Okay, so let's just pause. So calcium, where do you think that is?
Where?
Yeah, I mean, where here?
It's an even mass number, so it's spin is detectable.
Okay. Plus, so what would we use if we could use calcium NMR? What would we use it for? Do lots of the molecules that we're interested in contain calcium?
That we're interested in now.
No.
It's a very biological.
Yes. So if you were looking at bones density, maybe we could hope to look up calcium, but no, doesn't fit to this technique. Remember, what's a huge limitation of the NMR experiment?
It's one for specific nuclei.
Yeah? Okay, well that's what we're trying to do right now. Solutions. You have to make something go into solution. I think calcium really does that particularly well. It's why it's in bone, because it's not really soluble. If your bone's dissolved easily, then that would not be a good thing. I might point you in the right direction, or in a direction, not necessarily the right one. What elements on the periodic table are the framework of biochemistry?
Carbon.
So here's some carbon, and some hydrogen,
Nitrogen.
and some nitrogen,
Oxygen.
and some oxygen,
Phosphorus.
and some phosphorus, and maybe some sulfur. Mm-hmm. Only Michael said it wrong. He said schnapps.
Synopsis.
There's no reason why it can't be chinops. Okay, carbon. Can I do carbon NMR? No. Sounds like a big fat no, because carbon would be 6 protons and 6 neutrons.
Can you do like a different carbon?
Yeah.
So like carbon 13?
Carbon 12 has 6 of those, 6 of these, and 6 of those. Carbon 12 is the big abundant one. It is 99 point something % of all carbon that's out there. But what if we looked at that 1 in every couple of thousand nuclei? There was a carbon 13. This gets to be 6, 7, 6. This one is going to be spin 0. So that's like off. The spin of carbon 13 is spin half. It's a reasonable nucleus, except do I have its natural abundance? 98.9% natural abundance for carbon 12, right? So this is small, but it has nuclear spin of a half, so it is visible. But you're going to have to do the same experiment, the same observation over and over and over and over again. And we're going to do an experiment where we average noise to 0. Here's what we're going to do for carbon. And we'll talk about carbon in its entirety, because it's the second most used nuclei. Because I've got a sample, I'm going to need thousands, maybe hundreds before one of those carbons shows up. One of these carbons, carbon 13. So when I do my scan, most everything doesn't show up. Most everything is empty, silent. But in all of the noise, I might get something. If I do it again, and then I do it again, and then I do it again, and I average those. If this region, because it's empty, is noise. Noise is random. What happens when you average random numbers? Random numbers average to 0, whereas this tiny little peak, which is real, is going to reinforce. And so over the course of time, and I might need 256 of those, I might need 1,000 of them, I get this. We go into computerized average transients. Yes.
You keep on saying like 256. You said
Yeah.
last class, is that like a number? you
It's
make up, or is that
from
like-
the 8 times table.
Oh,
It's a computer number that because things are computerized, collection and bits are set up to be set up to be stacked in 8s. Now they're set up to be stacked in 16s, 32s, and 64s even. But it turns out that the people who design the instrument and the software and the interpretation and everything feel more comfortable if the data set fits inside what computer engineers think is a complete data set versus a number that doesn't fill their box and then they have to make an adjustment. The difference between 1,000 and 1,024 scans can't really seriously be anything. But yeah. 8, 16, 32, 64, 128, 256, 512, 1,024. These are all the computer numbers. So carbon-13, that's a nucleus. The isotope that we use, not carbon-12. What else could I do? Phosphorus. Which one? Phosphorus 30. No. You said 30. How many protons, neutrons, and electrons are in phosphorus 30? Yeah. So it has, well, phosphorus is mass, averaged mass number on the periodic table is closer to 31 than it is to 30. This would be 15 and 15. Two odd numbers. I've erased it now, but what does two odd numbers give me? It gives me an even mass number, which we know is not going to work out. So how about that one? Yep, phosphorus 31. I've done significantly more phosphorus 31 NMR than I have carbon NMR, which is not, I think, a typical NMR person's experience. That is visible. I don't think it's spin and a half. I think it might be spin 3/2. No, it's a half. And because when you look at the periodic table, phosphorus is quoted mass number is 30.97 something. That means this is highly abundant. That one's abundant, so that's a good nucleus. One of the things that we're going to do at some point during the day is take a look at the range of frequencies that we need to lock into. That's probably the only downside with phosphorus. Okay, anything else? Which other one?
I mean, you can do an isotope of nitrogen or oxygen.
Yeah, what about nitrogen? Nitrogen is position number 14 on the periodic table. It's not position number 14, it has an atomic mass of 14. I said that wrong. Which is 7 and 7 and 7. Two odd numbers combine to give me a mass number that is even. So I'm not looking for the even mass numbers, I'm looking for the odd mass numbers. If I click that up to 15, nitrogen 15, you can do the NMR of nitrogen 15.
So do we just have to always use isotope?
Yes. Yeah. Nitrogen 15 is spin half. But there's very little of this around. Very little. If you were to try to do a nitrogen 15 experiment on the naturally abundant nitrogen that is inside your molecule, you might be there all day. And you can't be there all day because everybody else needs to use the instrument, which means you would be there all night. They'll run the experiment overnight when there's nobody around. Yeah, there is so little nitrogen 15 in the world naturally. The other thing to do would be to get your sample enriched by sending it away to somebody that knows how to do that. Maybe Los Alamos in New Mexico. They could enrich it with an isotope that's not normal. Okay, all right, let's look at, we talked a little bit about the design of the experiment and the theory behind it, that there is a nucleus, it generates its own magnetic field. If you put that magnetic field inside a huge external magnetic field, then the nuclei line up, and then if you pulse the nuclei at 90 degrees with radio frequency, you knock them off their axis. They precess, so they resonate, and then they relax and precess back to their own place. Okay, we're going to look at that again two kind of slightly different ways. One of which involves a tiny tangential touch to quantum mechanics. It's called a quantum explanation, but it isn't really. I mean, other than it's this or that. In that way, it is quantized. Okay. So your nuclear spin has two components. It's really the spin angular momentum. Those two components are direction and magnitude. Magnitude is the italicized I that we were talking about before. It's written in some descriptions as an L. And then direction, which we're going to give as an M. And when I collect the M's together, I'm going to call them mu's. But we can just go with M for right now. Okay. Now it turns out that the values of m are quantized. It has values that run from minus I up to plus I, and they're in integer intervals. So you'd go minus I, you'd start at minus I, and then you would go minus I plus 1, minus I plus 2, until you get all the way up to plus I, if, you know, if we'd even need that number.
Those are all the italicized I.
Nope.
Oh.
No. There, see, that's where it becomes kind of difficult to read a little bit. The magnitude has values that are also quantized, and we'll see how many different variations of them there are going to be. I just say the h bar. Do I need the 2 pi? I don't need the 2 pi. It's Planck's constant. With a bar, h bar is the reduced form of Planck's constant. Which is h over 2 pi. I think most of the time we'll leave the h over 2 pi in it. Okay. Let's look at our most useful case. When you have a spin half nucleus. I have a nucleus. I have an axis right here that lines up with my external magnetic field. Magnetic field is given symbol B, and because this one is at the source, it's B0. So I have an external magnetic field of power B0. I have a nucleus here. And we will talk about having the electrons be point and precess like we did a week ago. That's going to set up its own little magnetic field. But what we're going to say is that it can only actually be in one of these two states. I'm going to allow the the nucleus to precess this way or that way, and when it relaxes, I'm not going, it's in one of these two states. Okay. My magnetic field comes this way, but any charged point object or any little object like this is generating its own magnetic field. At some point, if you are pushing downwards, you are resisting the magnetic field. So this is the higher of the two energy states. And the one that goes with the flow is the lower energy state. And the lower energy state has m, direction of plus a half, and the one that's resisting the flow has direction of m minus a half. These both have magnitudes h bar over 2. And that's because the way that you can tell how many states you have comes back to this, that the total number of magnetic states is 2 times I plus 1. So for a spin, nucleus spin, half nucleus, that is 2 times a half plus 1. It means I have 2 states. I'm going to flip between these 2 states. My nucleus is either going to, like, in its relaxed state, it should be going with the flow. It should be up here. But I can bring it into resonance, and at resonance it will be allowed to flip between those 2 states. But at some point it will be in this higher state. Okay. But I only have 2 options. Only 2 options.
Did you say mu and were the same thing?
Yeah, so I like using mu as a collection in its collected state. The m's are the individual, and then the mu's is the collection that describes these are all the possible things, and mu gets to be
Also,
the magnetic moment.
would it not be 3 states? Because of the parentheses?
No, I don't even know if that parentheses belong there. Well, it's 2i plus 1.
Okay.
No, hold on. I don't want to back out of that. So 1.5, it sounds like 3. So you have a part in the middle where it's 0, but no. So technically, mu is what they call the magnetic moment. We're not going to dwell on it. Okay, let's look at the situation where there are actually 3. Okay, so we can just, if you combine those 2 things together, so the magnetic moment, there's a couple of different ways of describing that, and I don't know that we're going to come back and do it, but the magnetic moment is equal to the product of something called the magnetogyric ratio plus the angular momentum. But the value here of that magnetic moment is these 2 things tied together, the product of those 2. So I get plus a half. Oh, he's got the magnetogyric ratio in this description. I can write that in. Okay. See, the more you look, the more there's another constant in there that we have to, oh, well, what does that one mean then? This is unique for each type of nucleus. So hydrogen has its own magnetogyric ratio, carbon has its own magnetogyric ratio. Let's do one that has 3. When you are an integer, when I equals 1, you're going to have 3 states. You're going to have one in the middle, where that value turns out to be 0. And then I'm going to have, so when m is 0, and mu relies on the value of m, and then plus 1 and minus 1. Okay, not particularly useful for us. If we had 3 over 2, then we get 4 states. And I have values of m that are plus 3 over 2, plus a half, minus a half, and minus 3 over 2. Our really useful stuff, though, is going to be in the world of the spin half. The gap between any of these states, if I write them out, let's do that again. Doesn't matter what the setup is. The gap between, so if I have, there's a half, I have 1, I is 3 over 2, I get 2 states, and they were plus a half, minus a half. I have a 0, plus 1, and minus 1, and then I have plus 3 over 2, plus a half, minus a half, and minus 3 over 2. The energy gap between each and every one of those turns out to be the same number. Difference in energy is the magnetogyric ratio times the reduced form of Planck's constant divided by 2π, times what the magnetic field is. If we do a little bit of rearranging, it's the same for all of them. Delta E also can just be written as h nu. E equals h nu, that's where Planck's constant came from in the first place. So we can rearrange this to give us what's become known as the NMR equation, because we're going to plot frequency on a scale. And that frequency, the frequency of my resonance, is equal to a constant, the magnetogyric ratio, which is inherent to the nucleus, divided by 2 pi, so that's just a constant, times the strength of the magnetic field. And that magnetic field is the one that you, this makes your answer, because this is at the source. This makes your answer instrument specific. If we had an NMR inside this room and an NMR in the next room, and we had a 200 megahertz instrument here and a 300 megahertz instrument next door, the frequency at which a methyl hydrogen resonates in this room would be different than the frequency that a methyl hydrogen resonates in the next room. But we're going to make it all relative by dividing everything at the end by the strength, the field strength of the magnet, and giving me a relative value. So this is my resonant frequency. That's the field strength of the magnet. And this is the magnetogyric ratio, which is a constant that is specific to the nucleus being studied. Which means, if I were to do the same experiment, because you are captive to two things. You're captive to the field strength of the magnet, and you're captive to the magnetogyric ratio. This frequency is going to depend on it. So if I use the same magnet, and it had a field strength of 2.3 Tesla, that would be my B0. Hydrogens would come into resonance at about 100 megahertz. Carbons, because they have a different magnetogyric ratio, would come into resonance at about 1/4 of that value. And phosphorus at about 30. Back when instruments were simple, this number's fixed, but we would sweep the radio frequency of the part of the instrument that initiates the resonance, and then listen for the individual nuclei to come into resonance. Nowadays, they do it all at the same time, and then we measure the free induction decay. So, from here, sample into resonance. Then my little individual magnetic moments are going to precess. They're going to loop around a bit. But some of them will be flipped into the higher energy states. And I can measure that two ways. I have X, Y, and Z. Z is the vertical axis. It's the axis that the magnetic field is lined up on. I can sum or average. It's going to give me the same kind of answer. What each of those little magnetic moments is doing. And because they're all pointing vector-wise upwards, it's there. When some of them go into resonance, that value is less.
The Z value?
Yeah. And then, over some course of time, I'm going to allow the nuclei to relax back. So that maybe I just have one down there in the excited state now, and so it builds back up until I get to be fully relaxed again. So this is showing and there is actually a reason why there's 5 of these. There should be 5. Yeah. So I can measure how much that energy changes on the z-axis. Or I can measure what the effect is on the other axes. So the pink value here gets to be what we'll call the resultant magnetization on the Z, and this one's specific to the Z. That's an MZ. If we look at what's happening on the X and on the Y, when it's relaxed, these are more spread out. And so I have the averages on the X and the Y kind of canceling each other out, but the Z is reinforcing. When they come into resonance, they precess, so I have a definite lining up here. Oops, it's not a particularly good pen. That value can be measured. And it's going to go from not being there to being real, and then it kind of goes away again. It fades away as you start to relax, it starts to fade away. That's the one that we're going to measure the most. This process of going away is called, actually, those are all still precessing. I've got to make that more random. Other color. This is called spin lattice relaxation. And remember, if I put my detector here to try and measure what's going on in the z-axis, then I'm going to be flooded with this because my magnetic field is pushing that way. So I'm not really going to measure what's going on in the z-axis at all. I'm going to measure what's going on at 90 degrees to wherever I pulsed. So if the magnet's on z and I pulse in at x, I put the detector on the y. And I'm going to measure that. And it comes out, it's just a big squiggle. It's just a bunch of noise, but it kind of decays. And that's called a free induction decay curve. And if I Fourier transform that, I can convert that into frequency.
And that's the graph of
And that turns out. So this is mxy over time, and I'm going to convert that into frequency. Fourier transform. If you'd like to know, I can tell you that I don't really want to. Don't really want to, but let's do it anyway. If this magnetization versus time curve is given by this function g in terms of time, then the Fourier transform that lives here is going to turn this f in terms of frequency is the integral from 0 to infinity of my original time-based function cosine 2 pi, that's a mu, frequency, time, changing time. That's what the Fourier transform does. And it turns magnetization versus time data into frequency data that we recognize as the NMR spectrum. And that's where we're going to get all of our proximity to electron withdrawal, chemical shift stuff from. Okay, that took too much time. We're going to look at two remaining things. So we know that there's an integration, we know that there's a chemical shift, we know that there is multiplicity. There are 5 factors that lead into what chemical shift is. We will hit those 5 factors quickly in the next lecture, and then We'll look at splitting patterns that obey the n+1 rule, which are called first order. That's not interesting. If it obeys the n+1 rule, then hey, great, that means you can interpret the spectrum. Okay, that's freshman stuff. We're going to look then at times when the n+1 rule breaks, and then we'll look at carbon NMR, and then we'll look at some two-dimensional NMR.